Hey, AP Chem. Hopefully your basic pH calculations were easy for you to figure out. What we're going to be doing now is we're going to be taking a look at the pH for calculating them when you have a weak acid or a weak base, because it's a little bit different. So just as kind of a review for you, if I asked you to calculate the pH of a 0.1 molar HCl solution, hopefully that should be pretty easy for you. If you remember, HCl, because it is a strong acid, and it's one of the 6 or 7 strong acids, when it hits water, it ionizes 100%. So whatever concentration my acid solution is, that is the concentration of my H plus or my hydronium ion concentration. And so the calculation, honestly, you should probably be able to do this without a calculator even. If I have a 0.1 molar solution and I take the negative log of that, I should get a pH of 1. Remember, it's 1 times 10 to the negative first power, so then it's a 1 for its pH. So it should be pretty straightforward, right? Hopefully nothing too crazy there. But if we take a look at example 1, it says, what is the pH of a 0.1 molar solution of formic acid? Now, formic acid isn't one of our 6 or 7 strong acids, and so we've got this Ka all of a sudden in our problem, and we look at this and we're like, well, let's think about this. It's an acid. I got a molarity. All I'm going to do is I'm going to put it into my pH equation like I did before, right? Totally going to be fine. 5 on the exam. I'm a professional. Tragically, that's not how it works. If you remember, weak acids only dissociate a little bit when they hit water. So this 0.1 molar concentration was the original concentration of the formic acid. It is unfortunately not the concentration of my H plus or the hydronium ion when that hits the water. You can see in this picture here, I only have a few white particles all alone there, and the rest of them are whole acid molecules, or the formate ion is what it's called. So we've got to do kind of a different process with this. And if you said to yourself, you know what, I haven't done in a little while is an ice table, today is your lucky day. So what we're going to do is we're going to work through this example, and then we'll kind of round back to 2 other things to take a look at, including what a weak base would be. So let's get into our doc cam and take a look at kind of how we're going to approach this. So again, the question is, what is the pH of a 0.1 molar formic acid solution? Our Ka is given to us here, and here is our reaction. So what I really like to do with all acids and bases in general is you really have to stop and think about what the heck is happening for the chemical process. And so since this here, formic acid, is an acid, when it gets together with water, we know that the acid is going to lose the H to the H2O. And so I'm going to have this HCO minus. And again, if you have the H, doesn't really matter in this case which one you take off. I just usually take off the one back here because it's from our carboxylic acids. And then it is going to make that plus H3O plus. So when we think about our reaction here, it is an equilibrium between this whole acid and then these ions here. And you're not going to get a ton of them because we do have a Ka value that's pretty small, but you will get some of them. Now, if I want to calculate the pH, though, I need this H3O plus concentration. I need that to get to the negative log of that number. So what I have to do is I have to figure out what my concentration of H3O plus is going to be at equilibrium. And that is where our good friend, the ice table, is going to come in handy here. So kind of through all of our ice tables previous, we know that I stands for initial concentration. And before anything breaks up, we have a 0.1 molar solution of the formic acid. Water is a pure liquid, so we're going to leave that out. And then because the problem kind of doesn't tell me anything else about these, I'm going to have just 0 and 0 for my concentrations here. So my change must be minus X, X, and X, because I have stuff to go down here and I have nothing, so I must have to make something here. And so my equilibrium values are going to be minus 0.1 minus X and X for both of my products here. Okay, so if I want to figure out what the concentration of my H3O plus is going to be, then I need to set up my equilibrium expression to solve with my Ka value. So I'm going to take my two products. Those are going to go on my numerator like we know. So it's products over reactants. And then it's going to be divided by HCOOH's concentration at equilibrium. And all of that is equal to 1.77 times 10 to the negative fourth. Okay. So if we think about filling in our equilibrium expression, I'm going to have X and 0.1 minus X kind of popping in here. And that leads me to X squared divided by 0.1 minus X. But if you remember with our 5% rule, and we'll double check to make sure it works, we're going to dump this X value to make our life a little bit easier and see if that works. So here's hoping. Okay, so when I go through and I take a look at the math here, I've got to get the X's alone. So I need to bring the 0.1 over here. So I'm going to multiply both sides by 0.1. And then I've got X squared equaling 1.77 times 10 to the negative fifth. And if I want to solve for X, X comes out to be 0.0042 molar. Okay, so that is my concentration of both of my products there. That's equal to the concentration of that ion, my conjugate base, and it's also equal to my H3O plus concentration. You kind of can't see that there. Okay, so it's equal to both of those things. Now, this is not entirely important for this problem, but this is going to be super useful. What I want to do before we get into calculating our pH is checking that 5% rule, because we got to make sure that this X here could magically disappear. So to check for my 5% rule means I'm going to take my X value, which is 0.0042 molar, and then I'm going to divide it by my original concentration, which was 0.1. Multiply that by 100, and you end up getting a percent that is 4.2%. So it's within that allowable range, so I can drop that X and it's not the end of the world. Means I can take this H3O plus concentration and find my pH. So my pH is going to be equal to the negative log of 0.0042, and that is equal to 2.38. So you can see the concentration of the acid is far, far less than 0.1 molar because it is a weak acid, and our pH is going to be 2.38 here. Now, as far as work that you are absolutely, in my mind, required to show would be the setup here with X squared equaling your K value, giving me your X value, and then finding the pH. So you don't need to show me all of this math. I think that's fine. If you can just go from the setup here to your X value and then to your pH, you should be good to go. One of the things you'll notice with these is that the ice tables kind of look pretty similar for a lot of these. You're going to have 0 and 0 for your products most of the time. You'll have your concentration. And so once you get the hang of this ice table setup looks almost the same for most of these pH problems. You really, if you don't need to, have to write that ice table even, but the reaction is really important. So you know the chemistry, so you know like what chemicals are here, but the actual setup of the ice table is going to be pretty similar. So if you feel comfortable skipping that table step, you can. If you like the table, more power to you. Okay. So we're going to return to our examples here so that we can kind of talk about a couple other scenarios you're going to run into. All right, so we did that one. All right, so here's example 2. Which 0.01 molar acid solution would have a lower pH at 25 degrees Celsius? Okay, so you look at this, we've got formic acid with a Ka of 1.77 times 10 to the negative fourth, it's the one we just did, or acetic acid with a Ka of 1.8 times 10 to the negative fifth. They are the same concentration. So if you think about your setup of your ice table, you are going to have the same setup for both of them. You will have x squared on the top and 0.01 molar on the bottom, but they're going to be equal to different things. So if you think about this, think to yourself which you think is going to A, have the higher H3O plus concentration, and then B, which one's going to have the lower pH. Okay, so stop and think about that for a minute. You can pause the video if you need to, and then we'll talk about it once you unpause it. Okay. All right, so if you think about it, the value with the higher Ka number, or the acid with the higher Ka value, is the one that's going to break apart into more ions. So if I compare these two, formic acid and acetic acid, because formic acid has a higher K value, it means that I'm going to get more actual H3O plus particles when it breaks apart. And so of the two of them, the formic acid will have the higher H3O plus concentration. That means that it is going to have a lower pH, because a higher acid concentration means a lower pH. So just kind of keep that in mind. You can kind of compare solutions if they have similar K values, and you should be able to kind of rank them based on their pH and their K values. Now, if I had an acid solution that was a strong acid, that one would by far have the lowest pH, and then you could rank them based on their other K values that they have. All right, example 3, which is really important to know how to do as well, is to deal with a weak base. So what is the pH of a 0.25 molar pyridine solution, C5H5N, if your Kb is equal to 1 times 10 to the negative 9th? Now you might say to yourself, how am I supposed to know that this is a weak base? The tip off at this point is that it says Kb up there, okay? So it's telling you that it's going to be a weak base, and the process of this is generally the same, but there's something a little bit different that happens that we need to kind of discuss. So back to the doc cam. And example 3. So the pH of a 0.25 molar pyridine solution, Kb equaling 1.7 times 10 to the negative 9th. So we have C5H5N, and because it tells me it's a Kb, that tips off me to what my reaction is going to be. So C5H5N plus water, if this is my base, means that water is going to lose a hydrogen over to this guy here. It doesn't matter where you put it. I'm just going to tack it on at the end, because the nitrogen is actually what's going to take that hydrogen in the first place. So it's going to be C5H5N, and I'm going to put H plus there, plus OH minus. If we think about phases, this is going to be aqueous, this is pure liquid, aqueous, and aqueous. So what's different about this one is that in my setup of my table here, I'm going to have OH minus instead of H3O plus, okay? Now, I will show you the ice table for this one, but you are going to see it is very similar to the one that we just had before. So my initial concentrations are 0.25 molar. I don't have any H2O, and my two products are 0. So my change has to be X, X, and X. And you can see this is a lot easier than solubility, because we all have coefficients of 1 here. So I'm going to have 0.25 minus X, X, and X. And then when I put this equilibrium expression together, I'm going to have my concentration of my conjugate acid, C5H5NH plus, times the concentration of OH minus, divided by my original concentration of pyridine. And that whole thing is equal to 1.7 times 10 to the negative 9th, okay? So setup is exactly the same. And this is why I said, I don't know if you need to show this ice table every time, because you'll see is equal to X squared over my original concentration. And then that's equal to my Kb value. Okay. So then it's an issue of solving for X. And I am fine, like I said, if you go from here straight to your X value. And that's what I'm going to do in this case, but I'll walk you through the math. I'm going to take this 0.25 and multiply it over. It doesn't hurt if you want to write this down, but it does save you maybe a little bit of time, but you got to be careful. So this whole thing here, forget it. I'll just write it down. X squared is equal to 4.25 times 10 to the negative 10th. And then if I take the square root of both sides, my X is going to equal 2.06 times 10 to the negative fifth molar. Now, because of the way that our reaction is set up, it is going to be equal to the concentration of my conjugate acid and my conjugate base. So that's equal to my concentration of C5H5NH plus and my OH minus. So when I set this up and I want to take the negative log of this, I am not taking the negative log of an H plus here. I'm taking the negative log of a hydroxide. That is a POH. And so there's one extra step if you are dealing with a base. So the negative log of 2.06 times 10 to the negative fifth is equal to 4.69. I'm going to put that into my calculator. And if you remember, pH and POH have to add up to 14. So if I want to find my pH from my POH, I'm going to take 14 minus 4.69, and that's going to give me my pH, which is 9.31. And if you think about it, that should make sense because you have a base. A base should have a pH above 7, and so our pH is 9.31. Okay? Like I said with these, there's nothing that you haven't done before with an ice table. It's just an issue of watching your chemistry for the reaction and setting up this expression correctly and solving for the right chemical. So if you have an OH here because it's a base, you've got to take that one step further. All right? If you have any questions, please make sure you get them cleared up. Otherwise, good luck.